Welcome to the Explainer. So, I want you to imagine, just for a second, a digital world where data literally lives forever. You'd have networks completely choked by zombie packets just endlessly circling the globe, server memory swelling up until the hardware physically crashes, and web pages eternally stuck displaying yesterday's news. Total chaos, right? Well, today we are looking at the unsung hero that actively prevents this digital apocalypse. It's called Time to Live, or TTL for short. You can kind of think of it like a Mission Impossible-style self-destruct sequence, baked right into the very foundation of our entire digital architecture. Okay, here is our agenda for this bottom-up evolutionary journey. Number 1, the digital expiration date. Number 2, network layer, preventing infinite loops. Number 3, web caching and CDNs. 4, Redis, in-memory cache control. And number 5, database lifecycle with DynamoDB. We're going to start all the way down at the low-level network packets designed back in the 1980s and work our way straight up the technology stack to modern, globally distributed enterprise cloud databases. All right, part 1, the digital expiration date. Before we can really grasp the modern applications of TTL, we gotta look at the foundational threat of stale data and infinite routing loops. So what actually happens if data has no expiration date whatsoever? Well, say a router gets confused and sends a piece of data back to where it just came from, and then that router sends it back again, boom, you get an infinite loop. Without a built-in mechanism to kill off these wandering zombie packets, our entire global network infrastructure would rapidly become congested and, honestly, be brought to its absolute knees in no time. That's exactly where Time to Live steps in. TTL essentially acts as a universal self-destruct sequence. It's a mechanism that limits the lifespan of data in a network or system, ensuring outdated info is automatically removed. It is a simple, elegant rule applied across the entire tech stack. Literally everything must have a lifespan. Whether we're talking about a quick network ping or a cached profile picture, TTL ensures that outdated or lost information is systematically purged from the system. Now, what's genuinely fascinating about this is how far back it goes. Check out this quote from the original DARPA Internet Protocol specification, RFC 791, from way back in September 1981. It states, if the time to live reaches 0 before the Internet datagram reaches its destination, the Internet datagram is destroyed. Over 40 years ago, the very architects of the Internet recognized that for data to survive, some data must be explicitly destroyed. It's just a beautiful piece of digital philosophy, isn't it? Moving right along to Section 2, Network Layer, Preventing Infinite Loops. Let's get down into the trenches here. Picture packets of data frantically bouncing between routers across the internet at the speed of light. They need strict supervision, right? Follow the perilous journey of just a simple ping packet. In step 1, host A sends a ping and attaches a TTL value, let's say 255. Every single time that packet hits a router, that router acts like a toll booth, but instead of charging money, it takes a fraction of the packet's life, dropping the TTL by 1. So 255 becomes 254 in step 2, then 253 in step 3, and step 4, if that packet gets lost in a loop and the TTL hits absolute 0, the router mercilessly discards it and fires an ICMP time exceeded message straight back to the sender. This simple little countdown is what prevents catastrophic network congestion. It's also kind of fun to see how this concept evolved. In the older IPv4 standard, this field was literally called time to live because originally it was conceived as a time limit measured in actual seconds. But routers process things way too fast for that to be practical. So when IPv6 rolled around, they renamed the field to hop limit. It's the exact same protective concept, just a far more accurate description of how routers are actually processing the data hop by hop. All right, Section 3, Web Caching and CDNs. Let's take a breath and move up the OSI model to the application layer. Up here, TTL stops being just a network traffic cop and becomes a highly strategic tool that actively saves your origin web servers from getting absolutely hammered by user requests. Notice how different content types require vastly different expiration strategies, using cache control headers to optimize your content delivery network, or CDN. Take versioned assets, like a JavaScript file with a unique hash in the name. Because that file name changes whenever the code changes, you can safely slap a massive TTL of 1 year on it. But public API responses, they might get just 30 to 60 seconds. That's just enough to reduce the load on your database while keeping the data relatively fresh. And user-specific data, like your private shopping cart, the TTL is 0. You never cache it, you never store it. Must always be fresh. Now, check out how this builds into an incredibly clever trick called the Stale-while-revalidate timeline. Imagine a user requests a page. From 0 to 60 seconds, it's fresh, so the CDN serves it instantly right from the cache. But what happens at second 61? The data is technically stale. Well, with Stale-while-revalidate, the CDN instantly serves the user the slightly old content anyway, but, and here's the magic, behind the scenes, it silently fetches the fresh data from your server so it's ready for the next user. It's basically a brilliant way to hide network latency from your users.
But configuring this whole shebang is a bit of a minefield. Look at these common CDN caching mistakes. Are your APIs making these expensive blunders? The absolute worst one, caching authenticated content. If your CDN ignores session cookies, you might accidentally serve user A's private sensitive dashboard to user B. Big yikes. Another huge mistake is forgetting to cache 404 error responses. I mean, if a broken link goes viral, every single click hammers your origin server. Setting a short TTL on 404s acts as a totally critical shield.
Moving on to Section 4, Redis, in-memory cache control. We are transitioning even deeper into the backend infrastructure now. Let's look at how TTL dictates survival inside an incredibly fast in-memory data store like Redis. When Redis memory fills up, it's basically a digital Hunger Games, and the eviction policy decides who survives. For most general web application caches, a policy called all keys LRU is exactly what you want. It simply evicts the least recently used keys, meaning the data your users are ignoring gets deleted to make room for what's trending right now. But here is the absolute golden rule of Redis caching. Every single key you store literally must have an expiration time, a TTL. Unlike a traditional hard drive-based database, Redis lives entirely in RAM. If you forget to set a TTL, your cache data will just grow and grow infinitely until the server completely runs out of memory and crashes your entire application. TTL isn't just a polite suggestion here, it's mandatory for survival. Finally, Section 5, Database Lifecycle with DynamoDB. We've hit the heavy lifting database layer. We're going to look at Amazon DynamoDB to understand the economics and lifecycle management of TTL at a massive enterprise scale. DynamoDB handles TTL natively, but it has very, very strict technical requirements. You can't just tell it, hey, delete this in 5 minutes. Nope. You have to define a specific attribute on your database item and store the exact expiration timestamp explicitly formatted as a number data type using seconds granularity Unix epoch time. It's super picky. If you use a string or milliseconds, DynamoDB's TTL scanner will just completely ignore it. Now, the absolute most important detail here is this single number, 0. Why? Because in DynamoDB, deleting data normally costs money, specifically write capacity units. But when you configure TTL correctly, DynamoDB automatically deletes the expired items in the background, usually within a few days, and it consumes exactly 0 write capacity units. Nada. Nothing. It is a remarkably cost-effective way to clean up massive tables of session data or old logs. And there's a fascinating downstream architectural effect to this too. When you're listening to changes in your database via DynamoDB streams, you really need to know why an item disappeared, right? Was it a user clicking delete, or was it just the system cleaning up? Well, DynamoDB distinctly flags these automated TTL expirations as service deletions. This is a real game changer because it allows your event-driven architectures to react differently, perhaps archiving that expired item to cheaper cold storage rather than permanently destroying it. So, from keeping ping packets from crashing the internet to saving your CDN from melting down to minimizing your AWS database bill, TTL really is the invisible pulse keeping your systems healthy. Which brings me to my final question for you. Take a hard look at your architecture today. What data in your stack is outliving its usefulness, eating up memory, and just waiting for a proper self-destruct sequence? Thanks so much for joining me on this explainer, and I will catch you in the next one.